Hello and welcome to 35th lecture of course on data-enabled tribological engineering from experiments to predictive models. The topic of this lecture is case studies in data-enabled tribological engineering. Let me start with the one case study. This is a case study 1 and we are picking one research article which was published in Mechanical Systems and Signal Processing, which was published in 2023. The topic of this paper is a digital twin driven intelligent assessment of gear surface degradation. We have already covered the gear related literature, and we know very well the gear pairs are very useful. They are of the compact structure and transmission efficiency is on the high side. We find various applications including wind turbines, industrial machineries, aircraft, space vehicles, land vehicle, almost all kind of vehicles also. So we'll start with the gear and then we'll move slowly to digital twin. First, we want to know why we are covering this kind of studies. We say very clearly the gear surface degradation assessment is very essential to estimate what will be the remaining useful life of the gears. It will help us to predict what kind of maintenance requirements are there. And this DT, this is a digital twin technology, will help us to address a gear we are monitoring challenges, where we are taking the data, we are correlating with our models, and we are correcting the mathematical model also, so that in future we are able to figure out virtual systems related to the physical structure. Or another word, we can say it can address the gear we are monitoring challenges by providing virtual representation of physical structure. It will help us to monitor real-time interaction between the physical mode and virtual mode. That's why we use the word sometimes cyber physical systems, because it helps us to evaluate the system degradation and estimate the residual useful life. Another thing, whatever knowledge we learn from digital twin models, in future we can utilize those for the design purpose also. That will help us to minimize the failure, minimize the friction, minimize the wear, and increase overall productivity. So this is a very important topic, and that's why we want to cover this as a case study in the present lecture. It's not a very new for us, reason being we have learned digital twin in a lecture 21, and then what we say that because we are able to observe all the parameters, so that will provide insight into the system behavior. How? We are trying to collect the data related to the real time, maybe pressure, temperature, displacement, vibration, acoustic, all those real data we are able to capture and able to analyze in situ. So that's whether we can really correct the whatever the condition need to be corrected. If it is a speed need to be corrected, load need to be corrected, or some sort of load sharing need to be corrected, or maybe weight properly, then it is possible. It also helps us to provide optimization opportunities. What is the meaning of that? Many times in process, we are able to figure out what is going wrong. So that's where we do data analysis. And when we do data analysis, we are able to identify the areas where the friction can be reduced, where rate can be minimized, and the lubrication possibilities can be improved. So in situ, all those things can be done. In addition, it helps to reduce the cost. Reason being, many industries they incur 15 to 20% cost in a maintenance. So cost reduction is possible because we can optimize the maintenance schedule. Not only this, we can really allocate the resources appropriately, optimizely, and then it will help us to reduce the unplanned downtime. It will not cause a failure, so we don't have to worry too much about the repairs. And then sometime we will need to replace a component, so we may not really keep in an inventory too many components. We can order whenever it is really required. We know the what will be the lead time and when the components will arrive, and we are able to forecast all those. So inventory costs also will come down, chances of repairs will come down, unplanned downtime will be also lesser. It will effectively allocate the resources appropriately. That's why we use a sometime word what we call a cyber physical system, and it is very very important for the tribology. Reason being the tribology is a dynamic, not necessarily the whatever I have designed today. And when we are placing in a system, it will have a similar kind of performance. Performance may deteriorate, sometime little more accelerated manner, sometime ultra mild manner. So we need to keep checking those things. And predicting tribology well in advance is very difficult. That's why the machine learning plays important role. That's why we are planning to think about a cyber physical system. So what we say, the modeling a physical system in a digital environment to simulate real machine behavior. And if we are able to find out and we are able to forecast, not only the find out, but if what will be the happening in a after say the 100 hour, 1000 hour, 10,000 hour, we are able to do it, then naturally it is going to help us. So it allows us continuous monitoring, controlling and optimization equipment performance. It enhances service management throughout the product life cycle. We know the product has some life cycle, and after that product need to be replaced or refurbished or utilized in some other system. And we see the digital twin of physical entity is continuously updated. It's not only the whatever we have designed initially, the equipment will remain similar manner based on the physical system data, that even the software will keep updating the cyber system, and that will really help us to get transfer the data between the physical system and virtual system or virtual entities. So what we say, essential knowledge in this case can be acquired using data acquisition and doing a simultaneously analysis of that, and after that we can estimate the useful life, and then we can really opt proactive approaches. Now, just to throw a little bit more light on a digital twin, I'm showing here the physical system which has been manufactured. This gear has been manufactured, and this was a cyber system which has been designed, and then we made a three-dimensional model. The question comes, in real situation, we know that this gear teeth will be subjected to pitting, subjected to wear, and there will be some other problems also. There may be possibility of the heat increase or increase in the temperature. So are we able to duplicate all those in this cyber system? That's important. So initially we do a training. That means if we have a data, we can train our digital system also. In other words, we start with the cyber system, we move to the physical system, we engage in assembly, in operation, then we get a data and modify the cyber system also. So it is a two-way process, and that's why we are using word the digital twin. Whatever happens to the real system, we are able to simulate in a cyber system. It will really help. There are a couple of papers available in literature. I'm not going to discuss this, but I'm just trying to highlight it. In this case, it has been shown a digital twin based state monitoring method of the gear test bench. Again, I'm not giving a guarantee that every publication which is coming into the literature is complete, comprehensive, but they have touched few good important points. So those need to be considered. In this paper, they have given pinion and gear dimensions separately. We can do some sort of a analysis and simulate and then do a fabrication. Not only this, they also tested whatever they are measuring the gear test bench temperature, they are able to simulate the similar kind of temperature. So there is a very good correlation between these two values. So whatever we are estimating the temperature. Now question comes, we have been doing this in earlier times also. We do a simulation and then we try to predict the same thing by experiments. But what's the difference in digital twin? Here, whatever the assumption if we made and then we are not able to correlate completely, then we are tracking back and trying to improve the simulation system also. So initially from a simulation we do fabrication and physical system. After that we are able to monitor all the performance parameter, required performance parameter. We are giving a feed to the cyber system or digital system so that the system can be corrected, and based on that we are able to forecast what will happen after month, after 2 months, and then again we are able to see that. And if we are able to prejudge, forecast that what will be the problem coming, we can really plan maintenance well in advance. That will really improve the overall productivity system. It will reduce the cost. It will reduce inventory cost also. So let's start now this lecture case study. We have already learned a number of things in related to gears, so I'm just trying to revise first those cases. Now let's see what in lecture 1 what we have learned. We have showed contact between the two gear teeth, one tooth of the pinion and another one gear, and we say that when they come in a contact, uh, at the interface there will be some sort of asperities, and there are three possibilities. One is the asperative breakage may occur, elastic deformation may occur, plastic deformation may occur. If elastic deformation, there's no variation, there's no change. But plastic deformation happens, naturally digital replica need to be changed. We need to provide that plastic deformation to the digital replica so that we are able to find a realistic situation. And if there are asperative breakage, again we need to provide those kind of information to digital twin so that necessary improvements can be made in a digital image. We also learn something that in the lecture 2, that before running in there is some surface roughness, after running in there is some other surface roughness, and we also learn the surface roughness plays very important role. So whenever we are predicting the performance or tribological performance based on the initial running in surface roughness or before running in the surface roughness, naturally we will not be able to estimate the temperature, pressure accurately. So that's why we require a dynamic calculation. We do initial calculation and then we require subsequent modification based on the data which we are able to capture from a physical system. So what we can say, throughout the lifespan of the gearbox, surface degradation comprises, because surface degradation will happen, and now it will have a two main points where it can be the adhesive wear, it can be abrasive wear, it can be any other kind of wear. Now here we are just because that publication we are referring, they have used a word fatigue pitting, and often we use the word as a fatigue wear also. So however in this case in the publication which we are referring, they have kept wear separately and fatigue pitting separately. So in short it will be wear and pitting. And then we say that it is inevitable. Wear will also occur because there is a mixed lubrication. Fatigue will also occur because there is a repetitive of the stress, and then the fatigue will be there. Thereby, it will be making some sort of a complexity in a gearbox health monitoring, and that's why we really require a digital twin for this. So, what we can say, assessing propagation of the gear surface wear. If we want to really predict, assess how the this surface wear will enhance, and then what will be the final shape. Naturally, we really require some sort of data, or we say we require some sort of a predictive maintenance, acquiring data, analyzing data, and thinking about the corrective actions. That's why we say predictive maintenance scheduling and averting abrupt shutdowns. So we are able to do it in well in advance, it will really help us. So these things have already been covered. We covered in lecture 13 some other type of the gears, and we say that why not we do a surface texturing of the various and the depth and various dimensions. Why do we do that? Reason being, the wherever there is a wear, debris will keep coming out of the surface. Now if those debris are not cleaned, it remain at the interface, then it will enhance the wear rate. So to keep wear rate lesser or minimum, those debris need to be dumped in this kind of a texture, and there is already some sort of and the dustbin available, and the debris will get dumped into this. Not only this, we also say that this kind of texturing is required to retain the lubricant, particularly whenever there is some movement, lubricant is not sufficient. Now if that lubricant is already available in this kind of reservoirs, then it will really reduce the friction and wear outs. So this is why we say the surface texturing is also important, and this was covered in lecture 13. we covered some sort of a lubricant monitoring. This is a offline monitoring, and we use a FTIR, which is to examine the what are the composition of the liquid lubricant, whether it has some sort of the moisture, or it has some sort of other stretches. That's what we showing here. There are some sort of oxides, or some sort of a degradation product. So we realize that if we do a offline analysis of oil, we'll be able to figure out whether oil is getting deteriorated or degraded or not. Even in presence of moisture, we know it is going to create a more moisture, or moisture will be related to the corrosion, and it can cause a corrosion of the gear surface also. So degradation of lubricant can be analyzed in offline mode. So this is also useful. Now if we do some sort of sensing, or we come up with a better sensor, this offline analysis can be shifted to the in situ analysis, and that will be helpful to the digital twin. That's why now that we have been talking something like a PS sensor, which can be integrated with the gear system, or gear setup, so that we can do measurement, in situ measurement of the pH level of the oil, and based on the pH level we can predict what will be the quality of the lubricant, and if this bad quality is happening, what is the purpose, what is the reason behind that. We can analyze it, and then we can schedule the maintenance according to that. And this was covered in lecture 15. We covered something in lecture 17, and that was related to variability in a wear data distribution. And we say there are many ways where the wear data will not be really giving a similar kind of results. Now here, because we have many test setups available, and one setup may give one kind of result, other setup may give another kind of results, so variability will be there. Then comes the operator methodology. So whatever the mathematical models which we generate, it may not give a right results always, or maybe the similar kind of results and across all the labs. So these parameters will also be important. Not only this, even the whatever the materials we are choosing in a different lab, the material may slightly change from one composition to other composition. So then there will be variability, because there is so much variability, and assuming we will be getting 100% correct data may not be correct. That's why we say in situ monitoring is very important. We can really design overall gear system, sensing unit, lubrication system, and engage. There will be some sort of variability. There we can use automated diagnosis process, and that is where it is really required a digital twin. So in digital twin, we have some initial calculation. Based on that, we are making physical system. Only thing is that after that, we are continuously monitoring the health, and we are doing the corrective action, and that's very useful. And this was covered in the lecture 17. Then we covered something on in a lecture 18, particularly offline monitoring of the prototyping testing, and we showed that there are the gears, and the gears when operated in normal operation, constant overload, cyclic load, and then for the different kind of hours, here the it has been shown that maybe the gear was designed and then they loaded 80% of the load, 125% means it is overload, 122 160% of the load. So this is overloading, and then they found some sort of a wear debris in this. If we are trying to analyze the wear debris, that's again offline. Wear debris analysis can provide some sort of mechanism what kind of failure is happening, and then they judge. They say that only few fatigue particles they observed. So, and because of the condition, whatever the condition they were posing, they found more sliding wear. That means wear was more dominating compared to the fatigue. So what we are studying in this wear and pitting, that means there was a lesser pitting, more wear. This depends on the situation, depends on the operating conditions. And then they also found that in only few particles were more than 100 micron sizes. So that means surface degradation was still in early stages. They run this for the 70 hours, and then they showed us a photograph in this way. So this will help us to understand the data, and then it will help us to make some the theoretical model or digital model in appropriate manner, and we can really improve the digital model, and then in future it will help us to predict the failure of the, or maybe say even the diagnose the fault which is going to happen on the gear surface. In lecture 18 also we moved from offline to online. We say why not we directly use the particle the sensing unit directly in an in situ arrangement. So that's why the wear debris monitoring sensor was engaged in a setup, and we could figure out what is the Fe, ppm level, iron ppm level, and then when we are operating for the longer duration, we are operating a shorter duration. So this was done, and then we say that if we are able to find the particles, can we develop an online system, diagnosis system for that purpose? That means we are collecting the particles, but we are analyzing those particles offline. We are getting online only the number of particles what we are getting in different basket, lesser than 40 micron, lesser than 60 micron, lesser than 100 micron. Those informations were we were collecting, but what will be the really characteristics of those data or those wear debris? Whether it will be related to adhesive wear, fatigue wear, pitting, so those things were not there, and that's why the online system was important from that point of view. So again, after that, we also did some sort of offline analysis. We say that whatever the condition, we should have some sort of algorithm. In this case, we found accelerated test event particles 8.86% of the more than 100 micron size. Particle size more than 47% belong to the particle ranging from 40 to 60 micron, and in this case, it was around 44% for 40 micron size. Of course, now what was the overall aim? To find out the number of particles which are coming out, and then here we were saying the size, and this is the number of particles per minute. If number of particles per minute are leaving and are going more than some threshold hold, then we can say the particles are or maybe the gear is undergoing the severe wear. So this kind of algorithm can be written, but again, there is a no definite rule that particle size need to be lesser than 40 micron, lesser than 100 micron, lesser than 400 micron. These are the subjective. It may vary from one researcher to other researcher, from one lab to other lab, from one company to other company, because there are many other parameters involved. Whether you want a life of the 20 years or life of the 5 years, it depends. So whatever our demand, whatever our requirement, based on that these data should be analyzed. So we are teaching the basic thing, but when it comes to the implementation, you need to take a right decision based on the situation which have been given to you. We covered in lecture 22 something like we are trying to connect wear analysis with vibration analysis. So that was covered in lecture 22. We showed one gear tooth, and we say that we can collect the data, and we are given example that the shaft is rotating the 6000 rpm having 18 teeth. So we really required a minimum 1800 data per second, and then if you are going for the more than one data per tooth, then we really require a 3600 flow data per second. And because there is some sort of variation in a AC motor, it will not give 6000 rpm exactly 6000 rpm. There will be some variation plus minus maybe say 10 rpm, or so in this situation you will get a lesser or more data, and that's why we have shown that in one cycle I'm getting 36,000 data, in other cycle I'm getting 35,940 data, and third cycle I'm getting 36,060 data. And if you do averaging, it will be a garbage. So that's why we emphasize that there should be a time synchronous averaging. So whenever we go for the vibration analysis, we really require a TCA, so that we are able to get a good results and a good average in this situation. So this was covered in the lecture 22. And why I'm repeating all this, because all these are required for a digital twin when we are making our cyber system model, and this data or this kind of information, this kind of knowledge is very essential for that purpose. We also study something about the filter in the same lecture. We say many times when we are getting the time based data, we convert to the frequency domain, and when we convert in the frequency domain, we can really separate or clean the data based on the required frequencies. Like in this case, we know that harmonic data are only required. So first harmonic, second harmonic, third harmonic, fourth harmonic, we really require only those data. So it can be utilize a band pass filter. We know exactly we require a data nearby and into FR, the shaft frequency, into number of teeth, then 2 NFR, then 3 NFR, then 4 NFR. So we really require the data related to that. Other data may be a lot of noise, so we need to denoise it. So we can use a band pass filter. Sometimes we really require a low pass filter, sometimes high pass filter. So depends on the situation. We can segregate the data, we can clean the data, and we can acquire the data which are very relevant to us, so that we require a lesser time to operate it. And we also covered something like we know there are some sort of side bands, and here we use a word residual errors. We know the harmonic will come, or the gear, in case of the gear teeth or the gear pair arrangement, harmonics will be there. Do I really analyze those things, or shall I go for the residual one? That means if there is a some harmonic signal here, I may not really require, because in a good teeth and bad teeth, both the time harmonics will come. Similarly, in this case, again harmonic will come, harmonic will come. So do I need this kind of analysis or not? But if there is a good tooth, then I may get a response in this manner only, or maybe I'll get a small, very small signal, which may be the kind of the noise. While it is the gear tooth is a damage, I'll get a little more sideband, so I can analyze it. So that's why the few researchers, they work on a residual errors arrangement instead of the main error or base error. So they subtract whatever the initial signal from a running in time signal. In that situation, we are able to highlight what is really going wrong. If normal case, whatever the signal we were getting, we are subtracting, so we will be looking at only the signal which are going on a higher side during running time, and that can happen whenever there is a damage. So pinpointing damage is possible. So there are methodologies, there are the algorithms which they, in which the residual errors are analyzed, and that will be also useful. And the residual signal we also showed in a similar lecture, when we are getting the vibration data and for the gear pair, and the maybe it's a 0 hour, we are getting some signal. At 40 hours, we are able to get some sort of signals in this case, and 100 hours we are getting shifting in the signals. So we by analyzing the residual error signals, we are able to pinpoint which gear tooth is going to get damaged. So in this case, suppose there are 18 number of teeth, and then we are doing analysis appropriately, even we can pinpoint, oh, the 16 number tooth is getting failure or some sort of a bad response. And that's why that when it was analyzed, we found some sort of pitting happening, and this, and some sort of edge loading is also happening in this gear tooth after 100 hours of operation. So this is possible, and this has already been covered individually to explain the complete the signal processing, signal capture and processing, and utilizing in a appropriate manner. Then we also covered something on the misalignment. We say that when we are engaging, there is a possibility of misalignment, and that was covered in a lecture 27. Then naturally there will be some sort of wear constant, and wear constant will increase if there is a misalignment. And in this case, we did some sort of slicing method. So utilizing this digital tools or algorithm, we can analyze each and every system. So if we are able to replicate, or we say if there is a misalignment, either we go ahead and analyze the misalignment, or we correct misalignment. Ideally, I believe that correcting misalignment will be better option compared to leaving a misalignment and then running it. But when we were trying to train our system, our algorithm, quite possible we may require some sort of a misaligned data also, so that in future system is able to predict, yeah, something is going wrong in the data, it is maybe because of the misalignment. Even vibration analysis is really helpful and judging the misalignment, so that can be also done. We also covered same lecture online gear wear monitoring of the particles, and we say we can use a CNN for that purpose. So all this algorithm, whatever I have described up to this, that have been covered in a paper which we are going to refer. and the paper is case study on a digital twin. That's what we see, digital twin driven intelligent assessment of gear surface degradation. So all the concept which we have learned in previous lectures, I'm trying to combine and then explain this kind of research publication. You can see here the digital twin model physical. Of course, they have not shown a complete model. They have shown some sort of signatures, and then after that, the complete physical system which they have made and then engaged. In addition, they did some sort of simulation, and this is what we are saying. This is a physical system. This is a digital twin, and it's based on whatever the digital twin based model we have generated. We made a physical system. After that, through sensors, we are able to measure the data, and we are giving those measured data to the digital twin so they refine it. After that, we can also utilize simulated data to go for the future prediction, and those simulated data can be analyzed using ANN. In this case, what we use in this case is transferring a knowledge, and that knowledge also can be corrected when we are having data physical system and can be compared with this, because whatever we are getting through the digital twin, we are analyzing it, we are giving input, and we are trying to predict what kind of pitting is going to happen, and through physical system we are collecting the responses, and then we also give that to the input or to the ANN. In this case, it has been used shown on the ANN. So whatever the simulated data, it is also predicting some sort of value, and whatever the data which we collected from a physical system, and that also being given as an input to this. So target data and source data, and that this is what we can say, the physical system basically will be targeted data and the digital twin will be source data. If source data is differing from a targeted data, naturally we need to update the system. If source data are exactly matching the physical system data or targeted data, that means we have replicated, we have duplicated complete physical system as a cyber system, and that's what the aim is there. So to duplicate whatever is happening in real system, physical system, same thing we are able to guess, we are able to estimate using a digital twin models. So this is what they have explained, and that's why we say now the major challenges. What are the major challenges? In this case, there is a number of interactions, dynamic interaction. It can be gear surface wear, dynamic response, lubrication condition, gear morphology, and this will continuously change its life. This is what I mentioned earlier. Traditionally, we used to design and make a physical model. After that, we can do some sort of monitoring to keep it healthy. But here now we are changing in digital twin. We are giving continuous feedback to the system again, so that in future we can predict. So in the situation, here the more science is getting accounted, not only experiments. Earlier we were doing the initial science, doing a design, making a model, and after that everything was left on to the experiments. And we know very well we cannot do infinite experiments. So we need to come back to the science, we need to come back to relation, we need to really judge what is going to happen. And that's where the digital twin is going to be play important role. And there's another one we are saying that when we design and after we do manufacturing, and there will be some sort of variation in manufacturing, not only in manufacturing variation, during installation also there will be, and then during operation also. That's why initially we were engaging everything. Some system were failing in a few hundred hour operation, and few system were running for the years and years. So we need to know why and how, what is really going wrong during manufacturing, during installation, during operation, right? With a digital twin, we are able to judge, we are able to predict those things and take a corrective action. That's very important for us to understand. And we see the development and utilization of the transfer learning, reason being whatever we are getting physical system data, and we are again going back to the digital model, and we say improve it. So there is a transfer learning from initially the cyber system or maybe the digital model, we are able to predict for the physical system. From physical system, we are able to predict for the cyber system. Again, from cyber system, we are able to predict for the physical system. So this kind of advantages to learn, and this is what we call a transfer learning algorithm. to use information acquired from a digital system to evaluate the surface wear of a physical structure, and this will be kind of well in advance. So today we are operating some gear pair, and using the digital twin model we are able to predict what will happen after 1000 hours. So we are able to do it well in advance. That will be useful. Now naturally, when we are training our model, we really require the data, and we really require data how the system will fail. Either we can pick up from a literature, which are already we have many failure case studies available. However, in this paper they utilize a two. We say the two run to failure tests were conducted. In one case, they did some sort of the two system. In one case, it was a lubricated system. In other case, they kept a dry case. So two cases were analyzed. In one, there is no lubrication, so wear will dominate. In other case, lubricant was there, so they assume the wear is not going to dominate, it will be fatigue failure and pitting will dominate. So that's why that they have done it. So they say to validate the effectiveness of overall system, what we developed this kind of two systems, and which they did to run to failure, and they acquired all the data to validate the model whatever they are making. So in this case, one more important point comes when we are doing installation. Foundation also plays important role. So we can incorporate everything in the model. That's one possibility. However, what they did a modeling of the foundation appropriately, and they got a signal. So whenever the foundation related signals are there, and then when we are running an actual case, you subtract that. After that, it will be related to gear pair system only. So if I want to analyze only gear press system, I acquire all the data, I need to subtract it and subtract from a overall system data. And we know foundation has some sort of characteristics. We are continuously getting those data and subtracting. That's one possible thing. Other one is that every time we do a kind of a modeling, and that the foundation modeling is also counted. So both options are available, both are possible. In my view, subtraction will be always a better option. It will clean the system, we will have a lesser inventory, lesser data, and then we can clean it properly. However, they used dynamic equations, and then they try to calculate the natural frequency FRF also in the situation, and then they use in this case the subtraction of the foundation modes to obtain the gear system models. So this is what they also did. They subtract the signals related to foundation from the main signals. Now question comes, how do we go ahead? As I mentioned that they did a two endurance test. Endurance test means run to failure. They did a two run to failure system, one with a lubrication where the pitting was dominating, other case dry, and they found that it will be abrasive particles because of the asperities that will cause of abrasive wear. That's an assumption. Could have been causing the adhesive wear also, but they assume that it is abrasive wear, and then what they did analysis on that. One more thing they use in this situation, they use a surface molding technique to find out whether pitting is really happening or not. So that technique also will be describing in next slide. They use analysis technique which we have already learned in surface analysis. So they have done optical analysis and to find out what will be the happening to the surfaces. Not only this, we can also find out some sort of friction data, wear data. However, they use a molds to find out the pitting related data. So when you are trying to utilize, you can use any technique. I'll prefer to go ahead with the vibration data, lubrication data, and the debris related data. While in this case, they have looked at only the this particularly lubricated case, they looked at only the mold related data. So figuring out what kind of the pitting is happening. In actual case, many other things are possible, but initially when you're training the system, you really require some assumptions and make a situation from that angle so the assumptions are satisfied. And then they found also the wear severity index or assessment. They collected the data in adhesive paper, so that all the debris particles which are coming out, they are getting collected. They found the mass of that debris, and based on that they could find out the what will be the volume. Again, in earlier classes we say weight measurement is not correct. Better we look at the geometry, and if we are able to look at the geometry, are able to analyze. Of course, To do that for the wear debris, it will be little more complicated, but I'm hoping in future that will also be possible, because these are the lubricated operating conditions. In this case, in a lubricated case, they applied a 20 Newton meter load and 20 hertz operating speed. In a dry case, they applied only one fourth of the load and 50% speed, so that wear rate is there. It should not be very high, then gear immediately changes the situation or conditions immediately. So they found it, and of course when we are using this data, we are finding the some sort of insight. We are able to really find out what kind of failures are happening, can be observed in pinion and driven gear, and it will really provide a comprehensive understanding of the gear wear. So this is what I mentioned when they did a dry case, no lubricant, and then they at the bottom you look at this paper was capped. So during a rotation, and whatever the debris will come out, will get collected on this adhesive paper, so that it will not fly, it will get collected. There is a chances it may fly also. It remains in environment, particularly small particles. Our assumption is that it will not be, and all part debris will be collected, and then they can measure the weight, and they can figure out what will be the volume, and based on volume they can do integration, and then can find out what will be the reduction in a thickness, which that will be also explained in the next slide. And then another one, they use a mold. You can see here that the mold has been capped on a gear surface. Surface pitting features can be duplicated on the mold itself. So this also will be explaining in next slide. Mold, you can see here they selected a few gear teeth and few pinion teeth, 1 2 3 here, and here 1 2 3. Now they applied this mold using the Microset 101 material. Reason being, they are saying that this is a very accurate, and then we can really go ahead with a low shrinkage, high resolution using this one. It has excellent wettability, a low surface tension, and then it can be removed easily because it has a low intermolecular forces. It has a flexibility to adopt the shape of the gear teeth. So this is what they, that's why they have selected the material Microset 101 as a mold, and then when it is attached to the surface, and it kept for the 25 minutes to the cure, and after the remove, you analyze that using some optical measurement or even SEM, then you can figure out what is the topography of that mold, and you can relate that mold topography with a gear tooth topography. And this was published in this paper. That's why we have given up the reference of this. These are some data. They are saying that it does has some hardness lesser than 1% shrinkage, thermal expansion coefficient. They did this 40 times, the total 40 times in this case, and then overall was a 68 hours running time, which covered around 3.25 million running cycles. So this is what they did, a 3.25 into 10 to 6 number of cycles and a 40 intervals. That means total 41 data will be there, so that they can train their ML model or ANN model, so predict the right result in the future. This is what we'll be showing, the two endurance test. This as a dry case, this is as a mold case. And if you want little more understanding of the molding, we generally do this kind of injection molding. We have die and punch system. Same thing they are doing here. They are trying to show the only the surface. That's why they use a flexible material Microset 101 to form the mold, and then examine it. This is a load situation and operating condition. Now in the situation particularly, they measured the weight of the debris, and based on that they could figure out what will be the volume. While in this case they use optical microscope, and then scanning confocal microscopy to estimate what will be the surface particle density. So here they are using the word density as such, that way they have been utilized. In addition, they try to collect the vibration signals, because finally vibration signals need to be related with a wear loss and the splitting density. So if we are able to relate the micro vibration signals, so in future whenever we operate in real situation, we will be getting a vibration signal, and based on vibration signal we need to understand what is really happening in a dry case, what is happening in the case of the lubricated case. and if it is somewhere in between, we can make some sort of other algorithm to interpret the results in proper way. So these data are important. These data are important to model digital system or cyber physical system. They adopted some model which is already published, and they use a Lundberg Palmgren morphotic model, which is here the SN was defined as a survival probability of the gear tooth at a specific rotation theta and number of cycles n. So this relation is already available in literature, and these are the constants C, M, H, which are also been defined in ASM handbook in 1992. This has been shown on here, and then we already have used Hertzian equations in earlier our lecture. Based on Hertzian equation P maximum, we can find out what will be the maximum shear stress. Again, this is assumption. So here they are taking another assumption. What will be the depth of the max shear? That's another assumption. And then stress volume. So they can find out these values. When you substitute and equate, they use a constant the way we were using initially, Archer constant. Same thing, they are now using the K pitting. That's a constant. And then they, because the logarithmic, that's why the overall is coming as exponential. And then they use a word surface pitting density to be correlated with the vibration signals, and that was defined d, that's the surface pitting density, as a 1 minus s, and then s can be calculated using this relation. Now if we differentiate, that will give what will be the increment in a surface pitting density. So this is a value, and if we differentiate to find out the increment, that is a d prime, particularly in this case differentiation of d with respect to number of cycles, and then they found this as an expression. So this need to be coded and incorporated in a digital model which we are making to estimate the pitting, what is happening to the gear. We also learn this shear stress related thing in lecture 4, and we say if there is a friction force on higher side, then this max stress will be on higher side and it will be on the surface. While if it is case of lubricated and a lesser and lesser friction, it will cause a lesser and lesser shear stress. Somewhat that is missing from this paper which they are mentioning. They are not accounted friction force, they are not accounted friction reduction because of the lubricant. So that's a one possibility when future people can look at, or maybe researchers can find out this one. So they integrated what is the difference when we are going with a cycle n to n plus delta n. It can be 2 cycle, 5 cycle, 10 cycle, depend on how fast we want to predict the results. And then overall they substituted, they found this as an expression. So d I plus 1 as a d initially whatever was pitting the density earlier plus this one, and then they found that this density will continuously increase first, after that it will be decreasing. Whenever density is decreasing, that means there is a time has come to change the gear. So that's what their model, they try to predict the model in this manner, and they have explained all those things in this manner. And now this is a overall flow chart of overall software. They say that measure the vibration, and you go ahead with the pitting model, you go with the Archer model, both the cases. In both the cases we need to use a contact pressure, that's a Hertzian pressure, which we already have described in previous lectures, and then try to connect with a real geometry, and then if you really require, go through iterations to solve it. So in other words, they find a vibration signal, they calculate RMS value. Similarly in this case they calculate IC_S2, and this is what we are showing here. The gear experience various stresses and wear event, each leaving a distinct imprint on the vibrational signals. That means what they are assuming, the vibration signals, based on the vibration signal we can find out the stress level, we can find out the wear events also. So they are trying to relate vibration signals with the stresses, or maybe say pitting and wear, or Orchard equation whatever we have. And then they say they need to collect RMS value of the vibration, and another one indicator of cyclostationarity, that is a IC_S2. This is what they have mentioned, that it is a, they have found these two parameters. If they measure through the vibration signals, they can relate with the wear analysis, and they can relate with the pitting value also. So that's what has been done. the tooth profile monitoring for the change in the thickness of the gear tooth can be related to RMS value, and pitting propagation can be related to ICS2. And this is what they have done, they implement it. And one more thing, they found that whatever the Archer equation, like we have a wear constant, it cannot be constant across all the cycles. Reason being, the profile is getting changed. Initially this is a profile, after that profile is like this dash dash. Naturally wear constant will continuously change, and that is need to be updated in algorithm. That's what they are trying to update the algorithm that way. And then they also use we can keep some sort of threshold when you are trying to integrate it in manner. You can keep some sort of limitation, or not necessary every time every cycle we need to update. We can update after maybe say few hundred cycles. So if you have some sort of threshold, that will be also a right thing. So in this case, the pitting we have shown here, the pitch circle diameter or pitch circle life, and here they are saying that it is a micro pitting, and then there is a possibility that we can really relate with the pitting coefficient. Pitting coefficient, that's what the assumption was there. But again they are saying the K pitting may be also keep updating it. It cannot be same. So they, to do that, they use a word Pearson correlation constant, that's a C, to find out what will be the K pitting. That's what has been shown in the next slide. What they took three data, dj minus 1, dj plus 1, in x as x coordinate, and this is what they measured. And then sorry, this is vibration signals ICS 2, in this case also it will be 2, ICS2, j minus 1, j and j plus 1. So they were taking a reading, and then this is a Pearson constant. And then this regression, if they were trying to analyze and then differentiate it till we get this constant as almost equal to 1. So this is what they mentioned, that correlation coefficient C as a function of K pitting, and then if K pitting is the same value, then there is no issue. But if it is a different value, then you need to optimize it. How do we optimize? Again, differentiate with K pitting updated manner, and then this is a C prime, which is a differentiation of the C. And that's what they have done. Maybe it can be number of cycles, or the way we have done for this D, similar manner in C girls case. So they have a given examples, step 1, step 2, step 3. In step C1, where they are measuring the ICS2 to identify specific pitting occurrence and the time, as well as whatever they define initially, it can be j is equal to 0. So first data, j can be 0, and then after of course this will be done only after the running in time. Reason being, before running time is over, there's a possibility the pitting density comes down, reduction happens. So they measure only after that. Once the running in time is over, after the pitting density will continuously increase till the failure occurs. And of course they are assuming that 20% will be the maximum density of the pitting, and if density exceeds the 20%, then there is a chance of the gear to be replaced completely. And then they already have a 41 data, because the 40 intervals are available, because they could collect from mold data, which was done for the 3.25 million cycle, or 3.25 into 10 to 6 cycles. That based on that they were doing it. And then using this kind of algorithm, continuously they were trying to update K pitting, so that whenever the K pitting is equal to the earlier cycle, they will not do much, they will assume same value. If it is not, then they will differentiate K pitting comes to the right value. So that's why we say when the surface pitting density start to decrease finally, it means a gear should be replaced due to the presence of severe surface pitting. So this is a what that their assumption. When we are doing a digital twin analysis, there is some assumption when the gear should be replaced. In my view, we should not look at the failure. We look at the what is really happening. Can we correct it? Can we change the lubrication flow? Can we change the lubrication type, or change some conditions? So the failure should not happen. We are going for more sustainability. While in this case, a digital twin, they initially train the model so that it goes to the failure side, and then train the model, and then whenever real situation, unknown situation, they are trying to figure out what will be the pitting density, and anytime pitting density going more than 20%, then failures are. This is what we say, that this is a 20% pitting density going more than 20%, then there is a need to change the gear. And they have analyzed using the ANN model, and then they try to correlate with this. So this is what they did for the initial one, but in real running condition, what are that? We have a dynamic model, we have whatever the degradation model also available, we have a real physical system. So this is what we call a cyber physical system. And as I mentioned, that whatever we predict from a digital model, it will be the source domain. Whatever we predict from a physical system, it will be target domain. And then this targeted domain and source domain data been provided to the CNN. They have used a CNN in this case. And then in CNN, you can see that convolution layer, pooling layer, conversion layer, pooling layer, convolution pooling, conversion pooling, convolution pooling, and after that the fully connected layer is coming. And all this have been already described in my earlier lectures. And of course they are using the max pooling operations, and then they, based on that, they are trying to also classify as a output. So this is what they have done initially with, that's what we say, transformation of degradation knowledge from digital twin simulation to real world evaluation was done. They use labeled data, that's a DS, unlabeled measurement, the DT, and they need to be compared with each other. Initially the training purpose, they use this convolution neural network, and this will try to extract the features. So that feature extraction is happening now. In this case, it can be the classifier C. Now you can really divide a number of debris, and then there is a comparison to be done with the targeted output. And then they use total 5 convolution models and fully connected module. In this case they use a loss function, because whenever we need to update, even we need to compare whatever there is a target data and source data, and then we need to compare, so that there is a minimum error. For that purpose they use a maximum minimum discrepancy loss function, so that the results are favorable and they can get a faster convergence in the situation. And finally, after once it is done, then this is ready to predict what will happen in real case. So this is what they made, an intelligent model, updating model in this case, gear system, dynamic model, and then they are comparing the results. And then when they compare and they find there is a correlation every time, dynamic model whatever compares, whatever the gear physical system compares, the model gives the results, these need to be compared with each other. And then if they are not giving the same FFT results, then need to be upgraded, and that is what we say, the model updating should be done in this manner. So what we can say is a basic procedure for the intelligent model updating approach has been shown in this complete figure. And then they use a word signal characteristics. As I say, that vibration measurement is happening. So in this case, signal characteristics in time domain, frequency domain, and natural frequency. So they were matching with 3: time data, frequency data, and natural frequency data. If they are matching with physical system and dynamic system, then there is no problem, and then otherwise need to be model need to be updated using the optimization algorithm. And then they also found there is some sort of discrepancies coming in degradation model and what they were predicting, whether they try to update that model and get a right results. So finally, when we want to judge whatever they have done is correct or not, this has also been what we say, this is the confusion matrix. Confusion matrix was taught in earlier classes. So they use a 6 category. What are the 6 categories, 6 groups? They created a 6 groups for vibration, and then they use 6 model having a different kind of pitting density. So 3% change in pitting density, then 6%, then 9%, then 12%, and finally they kept upper limit of the pitting density as a 20%. After that, gear need to be changed. So this has been done. And then what we say, that whatever the physical data which they were measuring, finally that name was given as a ground truth, to signify this has come from a measurement, it is not a simulated one. And they found accuracy something like a 94.8%. And now if you see the t psi also be given here, And this is a basically a TSI in this case is used for the dimensional reduction, the way we use a PCA. So this is the dimensionally reduction techniques for the better visualization. So you can see that the 6 can be converted to 2, and you are able to see there is a one cluster here, another cluster here, there is a some overlap, there's another cluster, and of course this overlap shows very clearly there is some inaccuracy that need to be modified. So these are the clustering, and this is the visualization, whether they have done everything correctly or not. So this is what mentioned, the data point that are close together in TSI visualization are likely to be each other in original high dimensional spaces, because TSI is what we are reducing the dimension, in this case particularly 2D has been done, and this all the results are related to lubricated test. It is not it is related to only pitting. That's why we are saying pitting severity assessment, and 6 number is a severe most pitting results. Number 1 is a ultra mild pitting kind of thing. So they are trying to judge. You can look at here, diagonal will give the what is a really true signals, the 100% comparison. So in this case 0.91, 0.991, 0.9, 0.93, 0.96, and overall accuracy is something like a 94.8%. Inaccuracy related to the, because we are getting some signals here, some signals here, and some signals here also. So there are some sort of inaccuracy, and then we know very well inaccuracy need to be judged based on the what is the precision, what is the recall, and that was covered in our lecture 24th. You remember that we try to compare debris which we collected in different category, whether cutting debris, spherical debris, fatigue debris, sliding debris, rubbing and debris, and we use precision. Like precision of cutting was related to 1, almost 100%, precision spherical 100%, precision fatigue was around 95%, precision sliding was a worst 83.3%. Similarly, in the case of the sensitivity or recall, we say the recall fatigue in this case 90%, recall sliding 93.75%, recall rubbing 95.83%, recall cutting 100%, spherical 100%. So we need to instead of looking only accuracy, we should have a precision level values and recall values also. So based on that, they say overall precision model in the case of 95.61% and recaller 95.92%. What's the meaning of that? Wherever like in this case we got a worse performance, here we need to know, yeah, we really require little more number of data related to sliding. We are not able to distinguish appropriately because this is 83%. So if I look at overall percentage accuracy, it was a 96%. Doesn't make much sense to us. But when I look at, yeah, precision, something is wrong in sliding, and we need to improve the results. Similarly, when we are coming to the recall fatigue, again we are able to find that there is a need to really change it, or we need to improve it. So instead of looking for the overall accuracy, it will be always advisable to look at the recall and look at the precision and improve the results based on that. Now coming to the severity of the wear, where they conducted the test related to dry, and they divided into 4 degradation stages. What is the meaning of 4 degradation? They say every stage has a 60 micron degradation. That means this is a profile, and if the next line comes to 60 micron, then that's a stage 1, 120 micron is stage 2, 180 micron is stage 3, something like that. So TSI, again, that the chart they have shown, we are able to see 1 2 3 4, we are able to see the clusters. So this indicates that they have done reasonably good job, and we are able to get a 4 different kind of thing. However, coming to the accuracy side, you can see this is a diagonal 0.92, 0.9, 0.95, 0.94. So accuracy is also very good. But if you look at the precision in related to first, precision is 93.9%, precision 90%, precision in this case is 3. That means there is some problem in judging 3 and maybe say 2 also. There is some sort of interdependence in this case. Same thing for the recall also, 90 and 93%. So there is some sort of variation. So maybe we require little more number of data to analyze in a slightly better manner. So with this, I see that we need to really dig into the case studies, and then we whatever we have covered in our earlier lecture, almost all the complete knowledge is very useful, and we include this to really understand any research article which has been published in the recent days. That will be really very useful for that purpose. So with this, I say thank you for attending this lecture. Thank you.